Some questions exist, not because they demand answers, but because they quietly reshape the way we see everything. How did the universe form? When did time begin? And where do we stand within this vast, unfolding story? This video is not only about stars, galaxies, or planets. It is not merely a catalog of cosmic objects. This video explores the birth of time itself, the first vibration of matter, and how emptiness became a stage where everything would later appear. Not through myths, not through guesses, but through measured data, careful observation, and the physical laws that govern reality. If you want to feel the universe not only when you look up at the night sky, but also when you try to understand what lies beneath it, take a deep breath now and return to the beginning. The story of the universe is far deeper than the human mind's familiar idea of a beginning. In everyday life, beginnings are events that happen within time. A sunrise, a birth, a moment that follows another. But the origin of the universe is fundamentally different. What we are dealing with here is not something that happened in time, but the moment when time itself came into existence. Concepts like before and after do not apply in the usual sense, because they only gain meaning once time already exists. When modern cosmology tells us that the universe existed about 13.8 billion years ago in an extremely hot, dense, and compact state, it is not describing a tiny object sitting in an empty void. Instead, it describes a condition in which all of space was compressed, where distances between every point were unimaginably small. This was not matter exploding outward from a central location. There was no center. The expansion happened everywhere, at once, in every direction. Every region of space today was once part of that same primordial state. This conclusion is not philosophical speculation. It is grounded in observation. When astronomers analyze the light arriving from distant galaxies, they find that its wavelength is stretched toward the red end of the spectrum. This redshift is a clear indicator that those galaxies are moving away from us. More strikingly, the farther a galaxy is, the faster it appears to be receding. This relationship, now known as Hubble's law, reveals that space itself is expanding. When these observations are placed within the mathematical framework of general relativity, a remarkable picture emerges. The equations describing space-time do not permit a static universe unless artificial adjustments are made. Instead, they naturally predict expansion or contraction. Running those equations backward in time leads to a universe that was once far denser, far hotter, and far more compact than it is today. The term Big Bang refers to this extrapolated early phase of cosmic evolution, not to an explosion in space, but to the expansion of space itself. As we trace the universe back toward its earliest moments, the familiar language of physics begins to falter. The first 10 to the minus 43 seconds, known as Planck time, represent a boundary beyond which our current theories cannot reliably describe reality. During this epoch, Temperatures reach levels measured in trillions upon trillions of Kelvin. Energy densities are so extreme that space-time itself is subject to quantum fluctuations. Gravity, which in general relativity is described as the smooth curvature of space-time, becomes violently turbulent at these scales. General relativity and quantum mechanics, both extraordinarily successful in their respective domains, collide here. General relativity breaks down under quantum scale fluctuations, while quantum theory struggles to define space and time themselves. This is not a failure of science, but an honest acknowledgement of its current limits. Physicists continue to search for a theory of quantum gravity, one that can unify these frameworks. But for now, the Planck epoch remains a frontier of uncertainty. Out of this uncertainty emerges one of the most influential ideas in modern cosmology: cosmic inflation. According to inflationary theory, the universe underwent a brief but extraordinary period of accelerated expansion, lasting only a fraction of a second. During this time, space expanded exponentially, increasing its size by an enormous factor. This process explains several otherwise puzzling features of the universe. Inflation accounts for why the universe appears so uniform and isotropic on large scales. Regions of space that now lie billions of light-years apart were once close enough to share the same physical conditions. Inflation stretched these regions apart before differences could arise. At the same time, quantum fluctuations, tiny random variations in energy present even in empty space, were magnified to cosmic scales. These fluctuations became the seeds of structure, eventually giving rise to galaxies, clusters, and the vast cosmic web we observe today. When inflation ended, its energy was converted into particles and radiation, reheating the universe to an extremely high temperature. Space was now vast, hot, and filled with energy capable of transforming into matter. Quarks, leptons, and force-carrying particles emerged in a dense, energetic plasma. The universe at this stage resembled a seething ocean of fundamental particles constantly interacting and transforming. Within fractions of a second, quarks began to bind together through the strong nuclear force, forming protons and neutrons. Meanwhile, matter and antimatter were created in nearly equal amounts. According to known physical laws, matter and antimatter annihilate when they meet, converting their mass into energy. If the universe had been perfectly symmetric, this process would have left behind nothing but radiation. Yet the universe is not perfectly symmetric. For reasons still not fully understood, a tiny excess of matter existed, roughly one extra matter particle for every billion matter-antimatter pairs. When annihilation occurred, that small surplus remained. Every atom in your body, every star in the sky, exists because of that minute imbalance. Understanding the origin of this asymmetry is one of the central unsolved problems in particle physics and cosmology, known as baryogenesis. As the universe expanded, it cooled. Within the first few minutes, temperatures dropped enough for protons and neutrons to combine through nuclear reactions. This era,
so-called Big Bang nucleosynthesis produced the universe's first atomic nuclei. Hydrogen formed abundantly, helium formed in significant quantities, and trace amounts of lithium were created. Heavier elements could not form at this time because the universe cooled too quickly and lacked stable conditions for more complex nuclei. The predicted ratios of hydrogen, helium, and lithium from Big Bang nucleosynthesis match remarkably well with astronomical observations. This agreement provides one of the strongest empirical pillars supporting the Big Bang model. It demonstrates that the universe's early history is not a theoretical abstraction, but a testable and measurable reality.
Despite the formation of atomic nuclei, the universe was still dark. Electrons remained free, scattering photons constantly. Light could not travel freely through space, making the universe opaque. This state persisted for hundreds of thousands of years until expansion and cooling allowed electrons to bind to nuclei, forming neutral atoms. This event, known as recombination, marked a fundamental transition. The universe became transparent. The photons released at this moment have been traveling through space ever since, stretched by cosmic expansion into microwave wavelengths. Today, we detect them as the cosmic microwave background radiation, a nearly uniform glow with a temperature of about 2.7 Kelvin. Tiny fluctuations in this radiation encode a wealth of information about the universe's composition, geometry, and early conditions. In many ways, the cosmic microwave background is the universe's earliest photograph. Following recombination, the universe entered a prolonged period, often called the cosmic dark ages. There were no stars, no galaxies, and no sources of visible light. Yet this darkness concealed a slow and inexorable process. Gravity, acting on the slight density variations left by inflation, began to draw matter together. Dark matter played a crucial role in this era. Although invisible to electromagnetic radiation, dark matter interacts gravitationally, forming the scaffolding upon which visible matter accumulated. Following recombination, the universe entered a prolonged period, often called the cosmic dark ages. There were no stars, no galaxies, and no sources of visible light. Yet this darkness concealed a slow and inexorable process. Gravity, acting on the slight density variations left by inflation, began to draw matter together. Dark matter played a crucial role in this era. Although invisible to electromagnetic radiation, dark matter interacts gravitationally, forming the scaffolding upon which visible matter accumulated. Over millions of years, gas fell into these gravitational wells. Regions of higher density grew denser, while surrounding areas became emptier. Eventually, the conditions within collapsing gas clouds became extreme enough to ignite nuclear fusion. The first stars were born. These primordial stars were unlike most stars seen today. They were massive, hot, and short-lived. Within their cores, hydrogen fused into helium, releasing immense energy. As fusion continued, heavier elements were forged: carbon, oxygen, nitrogen, and beyond. When these stars exhausted their fuel, they ended their lives in catastrophic supernova explosions, scattering newly created elements into space. This process transformed the universe chemically. Elements essential to planets, atmospheres, and life itself were no longer rare. They became part of the cosmic environment, incorporated into subsequent generations of stars and planetary systems. In a very literal sense, the atoms that make up living beings were forged in the hearts of stars. As stars multiplied, gravity drew them together into galaxies. Galaxies evolved into a rich diversity of forms, spiral, elliptical, and irregular, each shaped by interactions, mergers, and internal dynamics. Over time, galaxies grouped into clusters, and clusters into superclusters. On the largest scales, matter arranged itself into a vast cosmic web, composed of filaments of galaxies separated by immense voids. Computer simulations of cosmic evolution based on known physical laws and the presence of dark matter reproduce this web-like structure with astonishing accuracy. These simulations strengthen the case for dark matter as a fundamental component of the universe, shaping its structure from the earliest times. Just when cosmologists believed they were beginning to understand the universe's expansion, another surprise emerged. Observations of distant supernovae, used as standard candles to measure cosmic distances, revealed that the expansion of the universe is accelerating. Instead of slowing under the influence of gravity, space is stretching faster over time. The cause of this acceleration remains unknown. It is attributed to a mysterious component called dark energy, which appears to permeate all of space. Dark energy accounts for roughly 70% of the universe's total energy content, yet its nature remains elusive. It may be related to vacuum energy, a cosmological constant, or an entirely new physical phenomenon. Whatever its origin, dark energy will play a decisive role in determining the universe's ultimate fate. Today, the universe continues its expansion. Galaxies drift farther apart, stars are born and die, and cosmic structures evolve. The laws of physics, established in the universe's earliest moments, have governed these processes for billions of years with remarkable consistency. From within this vast and largely indifferent cosmos, a form of awareness has emerged, one capable of reflection and curiosity. Human beings are not separate from the universe, they are one of its outcomes. The same physical laws that govern stars and galaxies govern the atoms in our bodies and the neurons in our brains. Yet those laws have given rise to minds capable of asking where everything came from and why it exists at all. This may be the most extraordinary result of cosmic evolution. From elementary particles to complex structures, from chemistry to consciousness, the universe has developed layers of organization that allow it to observe and question itself. At some point in its history, the universe became aware. The video of the universe does not end here, because this is not a tale that has been told and closed. It is a process that is still expanding, still transforming. Every atom has a past, every star carries a history, and behind every answer, another question waits. If this video has made you look at the universe just a little more carefully, know that this was only the beginning. If you want more videos like this, scientific and quietly profound, don't forget to like the video, subscribe to the channel, and share your thoughts in the comments, so that when you look at the sky, you no longer see only stars, but their stories as well. See you in the next video.